Okay, this is a review of Chapter 3 in preparation for the final exam of MAE 3323. And as promised, I will go through and do a quick review of the chapter and what will and what will not be on the test. What I'd hoped to do was go through the chapter and just grab pieces out of this PDF file and paste them into a Windows document or into a Word document, and then give you that document as well. Problem is, while I'm doing the video recording, if my machine won't let me do the screen capture. So I can't drag and select things and paste them. So I'll have to do that as a separate step. So the videos will come first, and then the documents where I've done the screen capture will have to come second because I'll have to redo those. So very quickly, what are we going to talk about in chapter? So this is the Chapter 3 review. Chapter 3 was loads and stress analysis. A quick look at the table of contents. Equilibrium and free body diagrams, that's statics, shear forces and bending moments, that's strength of materials. That could be all over this exam. So certainly be ready for that. Singularity functions, we talked about more in Chapter 4, but the definition of the singularity of functions appear in Chapter 3, so we'll grab those out of here. Talking about stress, Cartesian stress components in Morse circle and 3D stresses in Morse circle, absolutely that will be on the test. Elastic strain, not so much, but uniformly distributed stresses, that's P over A, changes in bending, dq over IB, torsion, stress concentrations, pressurized cylinders, all that, yes. Rotating rings, I won't put on the test. Press and shrink fits, which really is just pressurized cylinders, cylinders applied differently. Yes. Temperature effects, no. Curved beams and bending, yes. Contact stresses, no. So let's see what we have. This is static, sum of forces, sum of moments, both equal to 0. What more do I need to say? There's an example in the text. Feel free to look at that. It just demonstrates statics. Shear and bending moments. Okay, we see positive and negative bending defined. We see positive and negative shear stresses defined from an example. Here we're showing a cut section. And so we would typically define the resultant shear and bending moment. And in this case, we're looking left. V is defined as the derivative of moments, or moments would be the integral of the shear. Not really much to say there. Singularity functions, skipping that for now. We'll have to grab those definitions, though, in Chapter 4. Okay, the Cartesian stress components. This one would be showing a general stress situation from which we formed our cubes. And in this case, we have 6 total stress components acting on the cube for the 3D situation, which would be 3 normal stresses and 3 shear stresses. These are the names of the shear stresses. If we're in a plane stress situation, then we have stresses on 4 surrounding faces, but on this z direction face, we have nothing. We have no shear stresses on that face, and we have no shear stresses pointing in the z direction. So this would be a plane stress element. Okay, from this we learned how to do Morse circle. From this we understand that there are really 3 Morse circles when we get to the principal stresses. Morse circle is derived here. I wouldn't grab any of these equations. I wouldn't expect to need them. But finally, the final equation for getting the principal stresses that we later on called sigma A and sigma B out of Morse circle, that came from plane stress, because we only get 2 of them from the plane stress circle. And it includes a location of the center of the circle, the average of the xy stresses, and the size of the radius of the circle that involves the xy stresses and the tau stresses. And the radius of the circle is shown here. And on the picture, we see the center of the circle formed by the average of the 2 sigmas, and we see the radius of the circle formed from sigma x, sigma y, and the tau. And so this is our 2D Morse circle. We would call the rightmost value sigma A. We call the leftmost value later on will be called sigma B. But then we remember the 3D circles. Of course, there would be a tiny one right there, and there would be a huge one here. And so for this plane stress problem, there would be a sigma 3 right here at the origin that would set the size of the 3rd circle. There are examples. Feel free to look at the examples. Now we show the general 3D circle. And this one shows that we will call the 3D stresses that define the circle sigma 1, sigma 2, and sigma 3. moving from right to left. And even if we have a plane stress problem and appear to only have one circle, we have to remember that we always have three circles. And we've highlighted that enough, I think. Let's see. Here's our equation that would let us solve for the principal stresses, sigma 1, 2, and 3, when we know sigma x, sigma y, sigma z, and we know the three-dimensional shear stresses. This is a cubic equation in sigma, and this cubic equation will have three roots to it because we've set it equal to 0. That will give us our principal stresses. Of course, our maximum shear stresses from each circle would come from the radius of each of those circles. Then I made a note, be careful even when nothing's happening in the third dimension. Why? Because we always have that principal stress at 0, which could make the largest circle the circle that passes through 0. Maybe it is, maybe it isn't. Okay, we defined strain, but that's not really going to be on the test. Uniformly distributed stresses, force over area, no big deal. A uniform shear stress, which could be calculated as a force over an area. We did make note that that is very, very hard to create that kind of stress physically. Okay, beam bendings. Here are the assumptions for which MC over I is a reasonable or the true statement. And this goes through and does a little bit to talk about MC over I, but I don't think I really need to say anything about that, other than the possibility of having composite sections, which means you have to build up the moment of inertia from the composite sections by doing a BH cubed over 12 for this, a BH cubed over 12 for that, and then use parallel axis theorem to combine them. I don't really anticipate asking you to do that piece on a test, but be ready to use moment of inertia on a test. We could have bending in two different planes, and then the stress at any particular point can come from the word superposition that we've now defined, and we can calculate the stress of the stress because of bending in the x direction, in the z direction, and bending in the y direction, using the two moments of inertia, just by adding together and being careful with the sign, because knowing which piece is which is in compression, which is in tension. Very little I need to say about MC over I. Beams with symmetrical cross sections. We didn't talk about that very much, so I'm not actually going to be testing you on that. But we get some weird deflections out of beams that are not symmetric. Shear stresses, this is VQ over IB. I'll find a picture and remind you of what Q means. Let's see. Okay, so here is the equation for shear stresses for beams and bendings, VQ over IB. Q is an integral from the place where you want to know Q to the outer fiber of the beam. It's an integral of y dA. And this integral of y dA, let's have a look at it. And we'll see an example in just a second. Let me find it. See if I'm finding what I'm looking for. Maybe I drew a picture for you. Okay, this integral of y dA, let's talk about it on this picture. Let's say I want to know the Q value here, and I want to know the shear stress here. I draw a horizontal line on the axis where I want to know that shear stress. Then I look at the area above it. And the integral, or the Q value, is the area above this cut line multiplied by the location of the centroid of that area above the cut line. So it is an A times the centroid location. And so what makes the shear stress interesting here is we've still got lots of area, and that y bar quantity is large, because the centroid would be right about where that dashed line is. Why would we have very little shear stress or very little Q at the top? Because although the y bar piece is quite large as it's going to get, the area piece is small. Now, why would we have low shear stress right below that cut line? Because Q would still be very large, but this quantity called B, which is the thickness across the section here, that quantity let's see, sorry, our largest shear stress would actually be in the thin section right below the cut. Because that B is small, that would make that shear stress large. Shear stresses in this section aren't too bad, but right below the cut, our shear stress is going to be very bad because Q is going to be large, but B is going to be smaller dividing by B. Torsion, change in angle, TL over GJ. Shear stress, T times rho over J, where rho is any radius within the part. Maximum shear stress for circular sections, TR over J. Copy and paste that, but don't really need to say anything about it. For circular cross sections, J is pi d to the 4th over 32. That's worth writing down. And as you know from the project, we can often get the torque if we know the horsepower, or if we know the power. In this case, this is a horsepower equation relating horsepower, torque, and speed. If we don't have a circular section, then we can calculate the maximum shear stress using a correction formula right here, where the B's and C's come out of this table. Okay, closed thin wall tubes in torsion. We're really not going to deal with that on the test. I'll let you have a pass on that one. The open thin wall sections, I'll let you have a pass on that one as well. Stress concentrations, we did talk about. I didn't put anything about it on the first test, but who knows, might show up on this test. The basic idea is when we have abrupt changes in cross section, we're liable to have an increase in the stresses, and so this would be a typical stress concentration factor chart. On the chart itself, there are some rules on how we interpret the nominal stress, because this stress concentration factor will multiply the nominal stress. So this one says, in this case, sigma 0 is F over W minus D, and this W minus, and then divided by the thickness as well. Then W minus D, I would call that the naive stress in the area of the hole by paying attention to the hole, but not having included the stress concentration factor. That's what this equation would be. To know the stress at the edge of this hole, we would then have to find the stress concentration factor, multiply that factor by this equation to get the true stress. That'll be true for all of these kinds of stress concentration factors. We'll always have the rules on what the nominal stress would be, to which we apply the stress concentration factor. Of course, we want to remember that in static loading, we only apply the stress concentration factor to brittle materials. And brittle materials, we would apply the stress concentration factor, except for gray cast iron, which is so junky that it already has its own internal stress concentration factor, and that's been taken into account in the material properties for it. That would be stress concentration factors. An example. You may look at the example. Stresses in pressurized cylinders. So the schematic here says we have a thick wall cylinder. We have possibly an internal pressure. We have an external pressure, which is different from the internal pressure. And we'd like to find the state of stress within the material caused by these pressures. And what we will learn is that there are stresses in the radial direction I'm moving my mouse. I think you can see that. And there are stresses in the tangential direction. The radial direction stresses would tell us that the radial stress at the inner fiber is the internal pressure. This isn't showing any external pressure, it's showing it equal to 0, but the radial stress at the outer fiber would be the external pressure, and then this would just blend in smoothly in an interesting way. In the tangential direction, we would have large tangential stress, or also called hoop stress, at this inner fiber, diminishing to the outer fiber, but even though the pressure is 0 at this outer fiber, this stress does not diminish to 0. These are the equations for the tangential and radial stress if the external pressure is 0. These are the equations for tangential and radial stress if the external pressure is not 0. If we have thin wall pressure vessels, then these equations simplify down to a tangential stress as given. We still have the hoop stress equal to the radial stress, but we don't have a separate radial stress equation. Stress in rotating rings, we also have radial stresses and hoop stresses or tangential stresses in rotating rings. I'm not going to be giving you any problems on that on the final, but there's the equation. Press and shrink fits are simply an application of stresses in thick wall cylinders. In this case, we have two cylinders, an outer one and an inner one, and there is an interference that can be measured by radius differences. This is called the radial interference, and so this delta means radial interference in the equations. And we're going to press the small inner diameter into this larger outer diameter, and this one will have to shrink. The inner one will have to shrink, the outer one will have to expand, so that this gap in delta will close. That's going to place a large internal pressure on the outer one and a large external pressure on the inner one. And we can use the thick wall cylinder equations to calculate those. Most important thing to be calculated is what is the pressure of interaction between this surface and that surface when they're pressed together. Okay, this is the pressure equation. And then once we have the pressure equation, and this presumes we might have different materials outside and inside. The simplified equation says we have the same material on the outside and on the inside. And this lets us calculate tangential stresses at the inside of the outer part. This would be the outside of the inner part. And it's usually that outer part that is in trouble. And the radial stress, of course, is the pressure. Temperature effects, you learned in strength of materials that parts will grow as temperature changes using we measure that with a quantity called the coefficient of thermal expansion. I'm not going to give you anything about that on the test. Curved beams, of course, are different than straight beams in that we get a shift in the neutral axis is one of the biggest changes because of the curvature. The neutral axis shifts, and we have a different equation for calculating the stress. Excuse me, it's kind of early Sunday morning. And so we'll have to find the location of that neutral axis, which leads to a difference between centroidal and neutral called E, the eccentricity. And then we have the stress equation. Okay, the location of the neutral axis, here's the most important equation for finding that. The location of the neutral axis is the area divided by an integral of dA divided by the radius. So total area divided by this integral dA over r. For odd shapes, we would actually have to do this integration. Of course, we have a table in the text for standard shapes. I would suggest you go ahead and put that table into your notes. And then here's the key equation for the stress. Sigma is equal to m times the y location where we want the stress, the area, the eccentricity, and the distance between the y location and the neutral axis. And when we compute bending moments, we're not going to use the neutral axis to compute the bending moments. We're going to use the centroidal axis to compute those bending moments. Okay, let's see. If we want the stress to the outer fiber, then y would be a location of the outer fiber, and then this would be the radius to the outer fiber. So these equations are substitutes for this one when we want, where C sub I and C sub O are the radiuses to the outer fiber. I have an example problem where we first learned that if we integrate for rectangular sections, we get an equation like this for the location of the neutral axis for rectangular sections, and it involves a natural log. After that, it's just a matter of applying the equation for stresses and calculating them. In this case, though, this hook not only had bending stresses from curved beam, but it also had axial tension stresses, force over area stresses, combined with the curved beam stresses. Here is that table showing the location of the neutral axis for various cross sections. It also shows the location of the centroid for various cross sections if it's hard to find. This is an approximation for the eccentricity and therefore an approximation for the stress that in some cases will work. I do not want you using this on a test other than maybe just as a means of checking your answer, but I don't want you to use these as your primary means of getting the answer. Contact stresses, whether we have spheres or cylinders, says there will be a contact area. Okay, theoretically, if the circles remain perfectly circular, that contact area would be 0. But as they deform, the contact area grows in size. Excuse me, another yawn because it's early Sunday morning. So contact area grows in size, and then there's a pressure distribution, and there's a full 3D state of stress of the contact area, and all of that can be computed and demonstrated by way of graphs, and I'm not going to be placing that on the test. And that ends chapter 3. And so the things that I commented on, later on I will come back and make a study note sheet for that you can then play with. So next video will be chapter 4.